everyone. You're watching ETH. This is a channel whereby we teach you mathematics, physics, and chemistry. So without waste of time, let me start with the lecture. Today, I'm going to be teaching physics. This is one of my favorite topics, physics. So I'm going to be teaching you guys a very interesting topic in physics. Momentum. I'm going to teach you guys projectile motion. I'm going to also teach you guys energy plus power. Now, I'm going to start by explaining the most important terms. The most important terms that we have to discuss is the two terms, scalar and vector. Now, what is a vector? A vector has direction. No direction on scalar. No direction. Right. A vector, examples of vectors, you have velocity. Examples of scalar, you have distance. You have, no, sorry, my bad. Distance is also a scalar, but I wanted to write something which is similar to velocity, which is speed. All right. Displacement. And distance. Yes, that's about it. That's about it. Now, a vector has magnitude and direction, and the scalar has no direction. It's only a magnitude without a direction. So what is momentum? Momentum is given by letter P. So momentum is given by mass times velocity. So what happens if you multiply a scalar by a vector, you get a vector. So momentum is a vector. It is a vector. All right. Now, what are the units for momentum? kg, which is the mass, meters per second. I think that looks easy and looks obvious, doesn't it? All right. Another very important term, we have impulse. Impulse, which is the change in momentum. This is equals to mv initial, or mv final minus mv initial. All right. All right. According to Newton's law, according to Newton's second law, to be precise, impulse can also be written in a form F times time. All right. Okay. And now, as we have said, momentum is a vector. Therefore, we always have to choose the direction. Always have to choose the direction as positive. We always have to choose the positive direction. Positive, right? Now, what happens? What happened to the momentum when two bodies collide? When two bodies collide, we have two scenarios that takes place. We have elastic collision and inelastic collision. Right. Now, elastic collision. I'm going to give a very nice example. If you, let's say, for instance, if you take a rubber band and pull it, if you release it, it will return back to where it was. What does that mean? It means whatever energy or whatever stretch you give it to it was able to restore. So whenever there's inelastic collision, it means there's energy restoration, which in this case, we're gonna term it kinetic energy. So whenever there's elastic collision, there's conservation of kinetic energy. Now, the opposite goes with inelastic collision. So with inelastic collision, there's no conservation of kinetic energy. As a result, with inelastic, we have kinetic, with final kinetic energy is usually less than the initial kinetic energy. All right. Moving right along. I also wanted to discuss projectile motion. In projectile motion, if you represent your projectile motion graphically, let's say for instance, if I start with displacement and time, with projectile motions, say for instance, if I throw a ball upwards, let's say this is a ball. If I throw it upwards at t0 initially, as I throw it upwards, that ball will have maximum velocity at that point. However, the displacement will be 0 because that's where the ball is starting to move. That's the point. Then when it starts to move, over time, after some time, your ball will reach the highest point whereby the velocity is almost 0. Where the velocity is 0, not almost 0, where the velocity is 0. At this point, V equals 0. V equals max. All right, at some point, after a long period of time, when you have thrown the ball, it will reach a certain point, and then comes back, and your displacement is decreasing. Always make sure that you choose the direction of motion. So in this matter, upwards is positive. Therefore, if you throw the ball upwards, it means your displacement is increasing. Now, when it reaches that point and it starts going back, it will go back to the initial position. And then if it bounces, so I'm gonna make an example with if you throw a ball and there's conservation of kinetic energy, for instance, collision. It means if the ball bounces, it will return back to the initial position because the energy is conserved. So on the second round, it will do the same thing and then comes back. All right. Now that is the displacement time graph. The displacement time graph. Now let us draw the velocity time graph. Okay, when your ball is moving upwards, it is moving at a positive direction. And as we have said, your ball will start at a maximum velocity, Vmax. All right, and then as it goes down, as it goes up, sorry, your velocity decreases when it reaches the highest point. This is where the velocity is 0, as I have indicated initially, and then as it reaches that point, it starts to move at an opposite direction. It starts to move in an opposite direction. So this is the negative direction. That's negative and that's positive. Velocity times time. Now, what happens when the ball bounces? And also note that as soon as the ball comes back, just before it hits the ground, it reaches V max, but in a negative direction. So this will be minus V max. All right. As soon as it hits the ground, this is what's gonna happen. Just bear with me. Just bear with me. All right. See, it hits the ground. It will go back to the initial speed, but going upwards. So upwards is positive, then it will do the same. Come back to reach that position there. That position. Then the cycle continues. And as you can see, the velocity is also conserved. It went back to the original velocity and also the original displacements. Right. Something that you have to notice is that the slope of the displacement time graph will give you the velocity time graph. If you determine the slope at that point, it will be at its max. If you determine the slope right there, it's actually 0. And also there as well, 0. The slope there, it's a minus, but it's maximum. Then it changes the slope all of a sudden, and then it becomes positive. All right. Now the slope of the velocity time graph will now give you so-called acceleration. Acceleration time. Now, the slope of the velocity time graph at that point, as you can see, it's actually constant. However, we have chosen upwards as positive. And something that you're gonna notice is that the slope from here to there is actually negative. This is a decreasing slope. So you will have a negative acceleration up until there. And this is the point of discontinuity. This is a point of discontinuity. So as soon as it reaches that point, it's a very quick jump. However, the acceleration comes back to the original position, comes back quickly. The slope is still the same. All right. Your gravitational acceleration is 9.8. All right. Now let's move on to work, energy, and power. What is work, or what is work done? Now, work done, it is a scalar. So the work done is done by the net force. So if you go to Newton's second law states that Newton's first law states that the body will remain at rest or continue to move at a constant velocity unless if the resultant force acts on it. Now, when a resultant acts on an object, there's work done. There's work done, which is a scalar. All right. And that work done is done by the net force. Right. Now, your positive work is in the direction of the net force. Or the net applied force. And for the negative work, negative work is in the opposite direction. The likes of friction. If you push an object, so your friction will exert a negative work on the object that you are pushing. Now, Newton's second law of motion describes how describe the magnitude of the force, which F is given by MA. However, let's say if we have a situation whereby you're pulling a box, if you're pulling a box, you will have all sort of forces. You will also have friction acting on the object. However, in this segment, I just want to show how we are going to resolve the forces, because it is very important to resolve the forces by breaking down the components, the X and the Y components, so that we can calculate the resultant force. As you can see, that applied force is at a tilted angle. So if it's a tilted angle theta, we have to find the X and the Y components. Now, how do we find the x and the y components. All right. Now do we find the magnitude of that force and the magnitude of that force? We have theta here. You will agree with me that I can actually transfer that force to here, and I will have an object like, I will have a diagram which looks like that with an angle. Now, we do have the magnitude of that of your hypotenuse, which is F equals ma. That's your applied force. Now, this will be your applied force acting perpendicular to the ground. And this component will be your applied force acting parallel to the ground. Now, this is what we know about the hypotenuse. We know that sine of theta, which is opposite divided by the hypotenuse, is given by F perpendicular divided by your F applied. So now your F perpendicular is given by your applied force times sine of theta. Now, the other thing that we know is that cos of theta is the adjacent, which is your F parallel over F. So your F parallel is given by cross multiply. The very same thing that we did here, we will cross multiply. So F parallel times 1, F parallel. F times cos of theta, that's F cos of theta. So now, if you want to find these components, the components in this direction, you're going to have to use that formula right there. Right. The other thing to bear in mind is the total work done. Now, the total, sorry, not the total energy of the system. The total energy of the system is given by kinetic energy plus potential energy, which is usually given by 1/2 mv squared plus mgh. Now, this is when we are talking about gravitational potential energy. As you can see, we have gravity and change in h. Now, we're going to recap the equations of motion. The equations of motion The first one, we have V final equals V initial plus GT. You will note that all my formulas are for projectile motion. Projectile motion. Projectile motions only. Right. Right. We also have V initial, change in time, plus 1/2 gravity times change in time squared. Now, if you take, okay, let me call this one equation 1, equation 2, equation 3. Now, if you take equation 2, if you take equation 2 and you take v squared to the other side, v initial squared to the other side, you will have v final square minus v initial square equals 2g change of y. Now, change of y is given by v squared minus v squared final minus v squared initial over 2g, which is gravitational acceleration. Now, gravitational acceleration is given by, your acceleration is given by change in velocity, velocity final minus velocity initial over time. And you will agree that 1/g is given by t over v final minus v initial. Right. I'm going to take that expression. We will have v. Now, for those who are doing mathematics, we will understand that this is the difference between two squares. V final minus V initial plus V final, and then V final plus V initial over 2. Remember that T right there, we must multiply it. And then over V final minus V initial. It's coming from here. We have replaced G, or the acceleration. Note that V initial, these two expressions will cancel each other, and we will be left with V final plus V initial times time over 2. So change in y can also be given by that equation. So we're gonna call that equation 4. Right. Moving right along. Now, what is energy? Energy is the ability to do work. Right. Now, what is power? Power, which is given by P, is given by, it is the rate of work done. It is the rate of work done. Therefore, something that you must bear in mind is that whenever there's no must go hand in hand with work. So there is no work without mass. An object must always possess mass. An object must always possess mass. I'm going to repeat it. The object must always possess mass. Right. We talked about impulse earlier on, and I said impulse can be given as the change in momentum, and we can use the Newton's first and second law. All right, with impulse was derived from the following equation. Now, it was derived from the equation of motion, which is used in Newton's first law. So this will be acceleration times time, right? Or let me write it as acceleration instead of a g, but it's the same thing. It is the same thing. Now, if you take v initial to the other side, you will have something of that sort. Now, if we multiply throughout by mass, we will get m v final minus m v initial equals to m a times change of t, or t, same thing. Now, I think this will ring a bell. If you go to Newton's first law, or Newton's second law in that matter, you will see there that force equals ma. Now, if force equals ma, we will have, this is a change in momentum. Momentum is given by mass times velocity. So this is a change in momentum. On the other side, mass times acceleration is force times the change in time. This is where it comes from. Now, guys, thank you for your time. Thank you for your participation. I'll see you on the next one. Thank you.